Hello everybody. Today we will talk about Grover search algorithm. Actually, Grover search algorithm can be applied to many problems, and one of the problem states that we have to search through a list of numbers for a particular item. Now, if we look classically to this type of problem, where we have to search for a number from a list, then there can be two scenarios in the classical approach. First scenario is when the list is sorted. So that means if the list is sorted, the best classical approach search algorithm we can apply is binary search approach, where we discard every iteration we discard half of the items and we go for the middle one, selecting either the upper half or the lower half depending on the magnitude of the search item and comparing with the middle number. Now, if we apply this type of approach, binary search approach, then the time complexity that we will get is order of log to the base 2n. But if the list is unsorted, then the problem further becomes complicated because there is nothing we can do, and the best thing we can do is to just search for one item at a time and for all the items. So in this case, when the list is sorted, the time complexity is order of n. But Grover gave an algorithm in which he used the quantum approach, and he was able to successfully obtain a time complexity of O order of under root of n. That means he achieved a quadratic speed up over the classical approach. Now, the various steps for the Grover search algorithm include: the first step is the equal superposition of the initial state using the Hadamard gates, and at this time we obtain a cat-s state. Cat-s state is an equal superposition state that we get after the application of the Hadamard gate to every single qubit, and that puts us in this cat-s state. After we obtain the equal superposition state, we apply to the phase flip oracle. Now, the phase flip oracle will flip the phase of the target state, and after phase flip oracle, we apply the diffusion operator. Diffusion operator will flip all the amplitudes over the mean. So, by the result of the diffusion operator, what will happen is that the target state, the probability of uh, achieving probability of the target state after the measurement will become highly likely, because it will amplify the chances of getting the target state more and more. It is quite possible, depending on the situation, that we have to apply the phase flip oracle and the diffusion operator, which together becomes as the Grover iteration. So we have to iteratively roll through these two operations to come near to the target state. Now, there are certain mathematical operations that happen, and we need to prove those mathematical relations. So, the first mathematical operation is the equal superposition that we achieve through the set of Hadamard gates. So, we apply the set of Hadamard gates to the all zero states, and we get the cat-s state, which is the equal superposition, where capital N is equal to the 2 raised to the power small n, where small n is the number of the qubits. Now, if cat-x is any of the computation basis state or the eigenbasis state, then if we take the inner product of x with s, that will come out to be 1 over under root of n. Now, because if we want to go simpler, then we apply the diffusion operator with the outer product of the all zero state, twice of the outer product of the all zero state minus the identity matrix. But actually, the full operator is twice the outer product of the s state minus I. Now we can obtain the full operator from this uh, 0 initialized state by applying the set of Hadamard gates to the left and set of Hadamard gates to the right uh, of the phase flip operator, of the diffusion operator. Then and it can be easily mathematically proven that this equation, which is twice of the outer product of the S minus I, is equal to this equation. Now uh, if we start with the outer product of S and we write the we write the ket S as H cron n, uh, this is the ket 0 state and this is also n qubit state. So this cron sign applies that we are applying the Hadamard gate to n to the set of n 0 qubits, and the other portion in the outer product is the bra of S, so which is actually the adjoint of this h of n and the ket 0 state, all 0 state. So if we try to solve this, because you have to apply here the property that the adjoint of the Hadamard is actually equal to the Hadamard gate. So when you apply that property and just do little bit manipulation, you will be able to achieve the full operator equal to the all 0 state operator twice of the outer product of the all 0 state minus I, and applying the Hadamard on the left and the right. Now we can geometrically visualize the Grover's algorithm. Now we have two axes here. One is the ket W and the other is the ket V. So ket W is our target state. Ket V is all other states except W. Now let us start from the ket S states, because we applied Hadamard gates to all the qubits. So ket S is the state where we applied the Hadamard gates, and ket S is the equal superposition state. To this equal superposition state we apply the phase flip oracle. So phase flip oracle will actually flip the target state. So whatever is the proportion of the component of ket W in ket S, that portion will be flipped by the application of the phase flip oracle. That's the first step is the equal superposition step. The second step is the phase flip oracle step. After you apply the phase flip oracle, we apply the diffusion operator to amplify the likelihood of the target state. So after these steps, after we apply the diffusion operator, we end up at this point where we get this D is the diffusion operator, U is the phase flip oracle operator, and we apply the diffusion operator. What this diffusion operator will do? Diffusion operator will flip the U ket S state over ket S and will take to this point. All right. So what happens is, then after we apply the phase oracle, which will flip the phase of the W component only in S, then we apply the diffusion operator and that will flip over the mean, which is ket S. So that means basically when we apply the diffusion operator here, diffusion operator will perform inversion about the mean. So it will take ket S as the mean and it will flip over this mean, and it will basically invert over this mean. So it will reach to this state of which I have shown as 3. Now after these steps we end up in state D U ket S marked by number 3, and the overlap with the W state has increased. Now if you see closely, earlier the state was ket S, so the overlap of the state of the quantum state with the W state was very less. But when we apply the phase flip oracle and the diffusion operator, the overlap with the ket W state, that means the target state, has increased after the Grover iteration. Now overlap with V state, which is every state other than W, has decreased. Now if you look at this point, the overlap with V state, if you look at the ket S state, the overlap with V state is significantly high than the overlap with the W state. But when we apply the phase flip oracle and the diffusion operator, the overlap with the W state has increased, whereas the overlap with the V state has further decreased. That actually proves the quantum amplitude amplification, which says that the target state likelihood will increase towards the target state, and the the quantum amplitude of the other states will be minimized as far as possible. Now the question is that how many times we should apply this phase flip oracle and the diffusion operator. So what happens if you look at this point, this black arrow, these two black arrows are basically, this is the W state, this is the ket W state, right, and this is the ket V state. In this case, so what happens, we start with the ket S state, which is the equal superposition state. Now we apply the phase flip oracle, then we get a rotation of minus theta and we reach to this blue arrow. After that we apply the diffusion operator, then the overlap with W will be flipped over about the mean, which is ket SW, and will reach to this blue arrow. So if the angle between the ket V state and this state, which is represented by the blue arrow, is now 3 theta. So therefore you look at the angles. When you start with the equal superposition state, the angle was theta. When you apply the phase flip oracle and the diffusion operator, the angle goes to 3 theta. Now if you apply another iteration of the phase flip oracle from this state, if you apply the phase flip oracle, it will reach to this green arrow, and when you apply the diffusion operator, this green arrow will go to this green arrow. So therefore this green arrow makes an angle of 5 theta with this ket V state. Now if you look, now theta is the angle between ket S and ket V. Theta is given by the overlap between the state ket S and ket W. So theta is the angle that is given by the overlap of W, overlap between S state and the W state, which is given by this angle, right? Sine of theta, that is sine theta, is the magnitude of the overlap. So this portion will determine the overlap of W with S. So this becomes the height of the overlap between W and S, which is given by sine theta, right? And sine theta is the magnitude of the overlap. So this overlap, inner product of S and W, is the overlap of S and W. So when you take the magnitude, so that is equal to the sine theta. Why it becomes equal to the sine theta? Because the length of this arrow, the length of these vectors is 1. So when the length is 1, that means the hypotenuse is 1 and the height is this magnitude. So we can calculate it equal to sine theta. So sine theta will be equal to this, which is given by 1 over under root of n. So length of the vector ket S is equal to, as I have already explained, the length of the ket S vector is 1. So when we calculate sine theta, theta is the angle between the overlap of S and W, and this length is 1. So therefore we get sine theta equal to 1 over under root n. But when n is very large, S is going to get closer and closer to V. So that means when n is very large, this equal superposition state will come closer and closer to V. So in that case, theta n is very large. So that means S is going to get closer and closer to V. So therefore theta will be decreasing. So in that case, when theta is very much less than 1, so therefore we can equate sine theta equal to theta. So that theta becomes equal to 1 over under root of n. So after first iteration, it goes to minus theta. So I have written down the iteration wise movement of the states. So at the 0th iteration, the angle is theta. This is corresponding to the equal superposition state. After first iteration, this becomes 3 theta, because after first iteration, that includes the phase flip oracle and the diffusion operator oracle. This angle becomes 3 theta. So if you go on repeating, after second iteration it will go to 5 theta. After n iterations it will go to 2n plus 1 theta. Now ultimately what do we want? We want this angle theta should be equal to pi by 2, so that it actually overlaps with the target state. So the probability of getting the target state becomes the maximum when it will overlap with the W state. That means the target state. So therefore this 2n plus 1 theta should be equal to pi by 2. So theta, we know that we have already taken it to be 1 over under root n. So 2n plus 1, 1 over under root n is equal to pi by 2. So if we solve it, and we would expect n to be very large value, so we will get it approximately equal to pi by 4 under root of n, which gives the number of iterations after which n is the number of iterations after which the state coincides or at least very close to target state. That's what we are actually looking for. So it needs to be emphasized here that Grover search algorithm will require order under root n queries. Classically, we saw that for an unsorted list with linear search, the best that we can do is order of n. So order of under root of n, if you compare with order of n, so there is a quadratic speed up we achieve with the Grover's algorithm. Thank you very much.